Welcome to This Explainer. Today, we're going to look right past basic C++ syntax to reveal the mathematical magic that makes three classic algorithmic challenges highly efficient. You know, we often get so caught up in the syntax itself, the brackets, the semicolons, the nested loops, that we totally forget software engineering at its absolute highest level is really just applied mathematics. So, we're going to unpack exactly how understanding the underlying math can transform slow, brute force scripts into incredibly elegant, high-performance code. Here's our roadmap for This Explainer. First, the magic of algorithms. Second, finding the greatest divisor. Third, decoding Armstrong numbers. Fourth, the square root shortcut. And finally, why complexity actually matters. Let's jump right in.
Section 1. The magic of algorithms, moving beyond basic syntax. As we're about to see, writing truly great code is all about recognizing mathematical patterns so you can skip unnecessary work. Section 2. Finding the greatest divisor. Let's look at a remarkably ancient trick to solve our very first algorithmic puzzle.
So, if you want to find the greatest common divisor, or GCD, of two numbers, amateur code almost always relies on slow, brute force loops. But professional code, it relies on the Euclidean algorithm. This is an ancient mathematical principle that leverages a simple but brilliant fact. The GCD of two numbers also divides their remainder, and that translates into absolutely brilliant, highly efficient C++ code.
Here's how that logic plays out in practice. We simply use the modulo operator to find the remainder, swap our two variables, and repeat until we hit 0. In our code, we just set up a while loop that continues as long as variable b isn't 0. Inside that loop, we capture b in a temporary variable, update b to be the remainder of a divided by b, and then assign our temporary value back to a. It's essentially this beautifully choreographed dance of variables that continuously shrinks the size of our problem.
By following those three simple steps, the loop elegantly bypasses all those unnecessary calculations and immediately finds that our GCD is 6. Just think about what happens here. 12 modulo 18 gives us 12. We swap, so a becomes 18 and b becomes 12. Then, 18 modulo 12 gives a remainder of 6. We swap again, making a 12 and b 6. Finally, 12 modulo 6 is exactly 0. At that point, b becomes 0, the loop terminates, and a holds our answer, 6. There's no checking every single number, we go straight to the mathematically guaranteed result.
Section 3. Decoding Armstrong Numbers. Let's take a look at a rather curious mathematical anomaly.
Consider this specific integer, 153. In the world of computer science, this number is actually something of a celebrity. It's often called an Armstrong number, or sometimes a narcissistic number. Now, if you pass this into a standard C++ function, it behaves like any normal integer. You can add it, subtract it, multiply it, whatever.
On the surface, it looks completely ordinary. But what hidden mathematical property makes 153 a true anomaly? Why do computer science classes and algorithm tests totally obsess over this specific value?
Well, the secret is that the sum of its digits, each raised to the power of the total number of digits, actually equals the original number. So, 153 has 3 digits, right? If we take the first digit, 1, and cube it, the second digit, 5, and cube it, the third digit, 3, and cube it, what do we get? 1 plus 125 plus 27 exactly equals 153. It literally reconstructs itself.
To verify this in our code, we don't just guess, we use a precise 4-step trick to isolate and mathematically test each digit. First, instead of converting the number to a string to find its length, which, by the way, is incredibly computationally expensive, we use base 10 logarithms. Doing log 10n plus 1 instantly gives us our digit count. Then we run a while loop, extracting the very last digit with a modulo 10 operation, adding that digit raised to the power of our count into a running sum, and then chopping off the last digit by dividing the whole thing by 10. Finally, we just check if our computed sum matches the original number. It's clean, it's highly mathematical, and it's ridiculously efficient.
Section 4. The square root shortcut. Let's look at our third puzzle and a truly massive code optimization.
If we want to find the divisors of a number, iterating through every single integer all the way up to n is a complete waste of time. I mean, imagine if your target number was 1 million. A standard loop would run 1,000,000 times, checking every single integer along the way. But math gives us a brilliant shortcut here, saving our computer from doing half the work, or, in the case of really large numbers, almost all the work.
The key is realizing that divisors naturally appear in pairs. Because of this, once our loop hits the square root of our number, we can just grab the corresponding larger divisor and stop immediately. Take the number 12, for example. 1 pairs with 12, 2 pairs with 6, 3 pairs with 4. Now the square root of 12 is roughly 3.46. Once our loop hits 3, we've already found all the small divisors. And since we know they come in pairs, if our loop variable I divides n, then n divided by I is the other divisor. So our C++ code simply loops from 1 up to the square root of n. For every valid divisor we find, we also just print the counterpart. By understanding the symmetrical nature of multiplication, we literally slash the processing time.
Section 5. Why complexity matters. Let's quickly synthesize the math magic we've uncovered today.
To actually measure the real-world impact of these tricks, we use big O notation, which describes how our algorithms scale. By utilizing logarithmic and square root time complexities, our algorithms skip massive amounts of unnecessary work. That is exactly what separates amateur code from scalable, professional software. Because the Euclidean algorithm slashes the remainder in every single step, it operates in big O of log min AB time, meaning it scales beautifully even with massive numbers. Counting digits mathematically gives us a time complexity of big O of log base 10 of n for our Armstrong checker. And by stopping our loop at the square root, finding divisors plunges from a linear O of n down to O of the square root of n. Let me put that in perspective. If n is 1 million, a linear algorithm takes 1,000,000 steps. Our square root algorithm takes just 1,000. That right there is the power of math.
And incredibly, despite these massive leaps in speed, all three algorithms require a minimal, constant amount of memory. That gives them a uniform space complexity of O of 1. We aren't creating massive arrays or allocating giant data structures to achieve the speed. We're just using a few basic integer variables like temp, sum, or count. We fully optimize the time without sacrificing any space.
So before you write your next line of code, ask yourself, is there a hidden math trick here that could turn a slow loop into an elegant, optimized masterpiece? Because as we've seen throughout this explainer, the very best C++ code doesn't just stubbornly push through the data. It dances around it using the fundamental laws of mathematics. So keep exploring, keep questioning that brute force approach, and always look for the magic behind the logic. Thanks for joining me on this explainer.